The organizers asked me to remind you that there will be a reception after the two talks. And the first speaker of this section is Luest, who will talk about strings and non-geometry.
Okay, thanks for the introduction, and also thanks to the organizers for inviting me to this very nice meeting. I guess we will change the subject now a little bit. This conference is called String Phenomenology, but now the emphasis will be a little bit more on the strings, and maybe only at the very last moment I can tell you how you could use this discussion for phenomenology, but I think this will be not so clear even. So my talk will be about strings and non-geometry. So this is the outline. Since I'm the first speaker on this subject, and a few more talks will follow now later by Ralph, and also tomorrow, I will give you first a short introduction to non-geometric flux compactifications, and then I will tell you about recent work we did, namely about two aspects of non-geometric backgrounds. First, namely, to get an effective action of non-geometric string backgrounds, and this is in collaboration with David Andriot, he's here, Magdalena Laufos, and Peter Patalong, who is also here and giving a talk, I think, tomorrow, as David is doing, and also then together with Olaf Hohm, and colleagues from Munich also wrote two interesting papers related to this discussion. And then in the next part I will come to some, I think, new geometrical aspects of these kind of stringy geometries, which have to do with non-commutative and also non-associative geometry. Again, this work was done in part together with Ralph, who is here, and maybe he will, I think he also elaborates on this. Then during the next talk, Andreas Deser, who is also here, with Eric Klauschin, who is also here, and also with Felix Rennecke. And then also the work was done in collaboration with Cesar Condesco and Ioannis Florakis. And I'd like also to mention that there's this paper by Ralph and Eric, it's the same day as this paper appeared, where they really emphasized on the non-associative geometry aspect of this story, which I think is very nice and very interesting, and I try to explain you what is going on there. So I think it is known, but I think one should emphasize this again, that in general geometry depends on with what kind of object you are testing it. So assume you take point particles to test your geometry, then at least in general relativity in Einstein's gravity, it turns out that point particles see smooth continuous manifolds. Of course, this concept is very nice, but it also leads to some problems, namely there are classical and quantum singularities, and therefore it is important to ask yourself, how do strings see geometry? How do strings test space-time? And in general, I think strings may see space and time in a rather different way compared to point particles. One hint, for example, in string theory is that there is a shortest possible length scale, which is the string scale itself. And then there are various ways to describe stringy geometry. For example, there's this notion of so-called quantum Calabi-Yau geometry, which is also related to mirror symmetry in worldsheet instantons. I will not talk about this aspect of string geometry. And then there's another way to formulate it, which is called non-geometric backgrounds. And also I think this issue of non-geometric backgrounds actually is not quite new. In fact, it is relatively old. So, for example, asymmetric orbifolds are prime examples of non-geometric string backgrounds. Also, covariant lattices or the fermionic constructions are in general non-geometric. But the way I will discuss it today is mainly based on this notion of T-folds. So I will also explain you what these T-folds are. And one of the new observations, which I've already mentioned, is that in this setting we will see that the stringy geometry, or the non-geometry if you like, will turn out to be a kind of deformed geometry, in the sense that space points, string coordinates will not commute anymore, and eventually even will not associate anymore. So there will be also a notion of non-associative geometry, which means that this kind of double brackets, which you would call here non-Jacobiator, but in fact they are really a signal of non-associativity, are also non-vanishing. As we will see, these effects are then indeed linked to the finite extension of the string to the string length. So if you wish, they are alpha prime effects, and they are really string effects and not really visible in any theory of point particles. Let me also emphasize that we will do this in the context of closed strings and not in the context of open strings. Of course, you may know that for open strings, non-commutativity was something which people discussed already for some time ago, and one new aspect is here that this will also now arise in the context of closed strings in some certain backgrounds and not only in the context of open strings. Okay, so what are non-geometric flux compactifications? I have given you already a few examples. To understand this, we will very briefly recall standard Riemannian geometry. You know all this. Riemannian spaces are, for example, flat space or curved spaces, positively curved spaces, or also negatively curved spaces like this. And Riemannian geometry mathematically is described by the concept of manifolds. And in general, to describe a manifold, one needs different coordinate charts which are patched together by coordinate transformations. So here the group of diffeomorphisms is the one which gives you the transition functions from one coordinate patch u to a different coordinate patch u prime. So I think this is very well known to everybody here, and one of the key properties of Riemannian manifolds is that the distance between 2 points can be in fact arbitrarily short, and obviously coordinates are commuting with each other, and this is precisely the situation where one is using point particles to probe distance in the geometry of space. Okay, so now we want to understand how extended closed strings, and I again emphasize closed strings, may possibly see the geometry or the non-geometry of space, and therefore we will now also need to generalize the notion of a continuous manifold. And just to give you the idea, the main idea of this, we will encounter basically two very interesting situations. The one situation is called non-geometric Q fluxes, and I will define this even more property later on. But Q spaces or Q fluxes are string backgrounds which are still, at least locally seen in every local neighborhood of the space, Riemannian manifolds, but there are some global obstructions to define them or to treat them as manifolds. So globally they're not anymore manifolds, and the more proper mathematical description is that now the transition functions between two coordinate charts are in general not anymore only diffeomorphisms, but they include also the transformations which are called T-duality transformations. So we replace diffeomorphisms by also the group of T-duality transformations which are elements of the group SOD, D. And the new observation in this context now is that the Q space in general will become non-commutative.
So SOD is discrete or real?
It is discrete. It is over the integer number thing. Mm-hmm. Right. So it's a stringy non-duality, stringy T-duality symmetry. Okay. There will be even one more peculiar and less clear space or background, which is a non-geometric R-flux space. And these are spaces which I cannot even describe anymore locally by ordinary manifolds. So they're even locally not anymore manifolds. So we do not really know what we have in terms of geometry, and it's also not so clear how really to get them. I will come to this point, but at least these R spaces are also, I think they do exist, and they are round, and I will like to give you some arguments that these R spaces in fact become even non-associative, in the sense that this double commutator, this double bracket, which is defined like this, plus all the permutations, is non-zero, and this then tells you that associativity, even associativity, is lost in this kind of stringy background. Okay. On the other hand, since we are dealing with strings, with extended objects, the physics, the underlying physics, if you compute, say, scattering amplitudes, and I think Ralph will also tell you more about this, is nevertheless smooth, and everything is, of course, very well defined. So, I like to be a little bit more precise. What is a Q space, a T-fold? I told you, and people use also the notion of T-fold for these Q spaces. I told you that patching charts, one is using T-duality, and there's one nice and convenient way to construct those, namely as so-called vibrations. So imagine that you have a base space, which is called U, or patches of a base space, U and U prime, and over the base we have a fiber, in the easiest case a two-dimensional fiber, which is a torus, and then we have to give you I have to give you a prescription how we glue together the fibers if you move around the base. And for geometric backgrounds, indeed, so now I can look at transformations on the background which defines the fiber, which I call E, which is basically just the sum of the metric and also antisymmetric tensor field. And now for geometric backgrounds, I told you the patching is done by the group of diffeomorphisms, where these elements which act on the fiber parameters are just elements of GLD. However, for non-geometric backgrounds, you include also now T-duality transformations acting on E. Namely, you include also in general these non-linear transformations which do the patching in the overlapping region. And then, of course, it is, I think, obvious that this generalizes the notion of a manifold, because these include, for example, transformations which glue together a big torus with a small one, and this is not possible in standard geometry, but it is still allowed in string theory, because these transformations are still symmetries of the string theory if you include also stringy effects, stringy modes. Okay, I can give you a very concrete example of a Q-flux space. So in this simplest example, you have a base which is a circle, so one-dimensional, and the fiber is two-dimensional, as I have told you. Locally, it is still a manifold, so therefore, indeed, I can give you locally at least a metric which has simply the simple form, and you see that basically what you have is that the metric depends only on the coordinate x3, which parameterizes, which is a coordinate on the circle, and the fiber then depends in this peculiar way on the base coordinate, namely on the circle coordinate. And there's also a B field in this background. But now it's an easy exercise to show that if you go around once the circle, you really have to glue the torus by a T-duality transformation. So this background is only locally defined. And if you work it out, if you shift x3 by 2 pi, I have set the radius of the circle equal to 1, you indeed see that the parameters, the background of the torus, the metric, and the B field of the torus, namely G plus B precisely, is changed by this transformation, which is an element of SO d. So this is a Q space. Good. So to be a little bit more precise, I want now to consider, and this is another very important ingredient, not only the T-duality plays a role in defining those spaces. So this is the one role of T-duality here. T-duality also can connect various spaces which look rather different from the point particle point of view. Namely, in general, or for many examples, there is a chain of T-dualities which can even connect geometric and non-geometric spaces, backgrounds among each other. So I like to introduce the following chain of 3 T-dualities, and these connect spaces with different type of, say, flux background. So let me explain you this. We can start, for example, with a space which has a flat metric, but it has only supports a non-constant H field. So we turn on this particular Navier-Schwarz H field background. Then one can perform a T-duality, say in one of the directions, call it x1, and then you get something which nowadays is called a geometric flux, namely a so-called twisted torus, which is a curved manifold without a B field, but it is still a nice Riemannian space. Again, you can perform another T-duality, and then you will end up in the so-called Q-flux background, which is non-geometric. And finally, you can do also a T-duality over the remaining direction, which I have called x3. And you may have you may remember that in the example I have given, the background depends on x3. So following general wisdom, this is not anymore an allowed T-duality transformation where you can use the Buscher rules. However, with some more formal prescription, you can still try to do it. And I will indeed in a few moments introduce a framework to you where this is still possible, and then you end up with something which is called the R background, namely the non-geometric R flux.
Going from omega to Q, why is a standard T-duality in the x2 direction?
Yes, it is.
So why do you move to a non-geometric?
Well, it turned out to be that
you will be a big T field in the.
Yes. So if you I could show it to you maybe afterwards. If you have this twisted torus, or also called nil manifold, and it's known that its T-dual indeed is already a non-geometric background. So T-duality connects geometric with non-geometric spaces. And this is also, I think, already in itself an interesting observation. Okay, so I just maybe repeat. Here we start with a flat 3 torus, and then we have the twisted, curved Riemannian 3 torus. Both are still commutative. Then with the next T-duality, we come to the non-commutative T-fold with Q-flux. And finally, after the last T-duality, which is more subtle, as I told you, we get the non-associative space with R-flux. So this is maybe a bigger picture of all this, and indeed there are examples where you can realize this picture. So this was my introduction to this kind of non-geometric spaces, and in the second part of my talk I like to show you now how you can obtain an effective action for these non-geometric backgrounds. And this is, at first sight, this really seems to be a complicated problem, namely because if you look at the standard effective action of a string, say in 10 dimension, which is given here, it contains the metric, the Ricci curvature, and the H field. It is clear that this action in a non-geometric setting, in the way I've explained it, doesn't make any big sense, because if the metric and the background fields which appear in this action are not well defined, say not globally well defined or even locally well defined, then also the entire action doesn't make sense. The entire action is also not well defined, and this then cannot be the correct effective action of these non-geometric backgrounds. But on the other hand, we know that the non-geometric backgrounds do exist in string theory, and therefore you ask yourself, what is then the effective description of these non-geometric situations? Okay, so this is a problem, and indeed it was possible to write down a well-defined, even 10-dimensional effective action for non-geometric backgrounds. This can be constructed, and this is a work with these people which I have already mentioned at the beginning of my talk. So what is the mathematical framework? And I think the most beautiful and the most convenient mathematical framework, in my opinion, is so-called doubled field theory. Doubled field theory, I will explain it briefly on the next transparency, is something where you build in T-duality from the very beginning. So it's a formulation of string theory where everything is done in a manifestly T-duality invariant way. There is maybe also a different way to see it, namely a way where you can perform certain field redefinitions. This is how we did it in our first paper, but basically I think the mathematical framework which underlies this is doubled field theory. So let me give you a very quick reminder about T-duality. T-duality in the simplest case is a transformation which acts, say, on the radius of one-dimensional circle. In this way, it inverts the radius, and at the same time, it inverts or it exchanges also the so-called Kaluza Klein quantum number m with the winding numbers n of a closed string moving around this circle. You can also introduce momenta and dual momenta which correspond to the Kaluza Klein and the winding numbers. And if you now write everything in terms of left and right moving variables, you see that the left moving momenta are transformed in this way, whereas the right moving momenta just get a minus sign in this context. And since we have introduced momenta and winding, so momenta and dual momenta, it is also very natural now to introduce coordinate and dual coordinates, where the dual coordinates on the worksheet are just here the difference between the left and right moving coordinates. And now it is easy to see that T-duality exchanges coordinates with dual coordinates, or you can also write in terms of left and right moving coordinates, and then it's this simple action. So whereas on the background, this is important, T-duality acts in a nonlinear way. If you double your degrees of freedom, if you double your coordinate space, you have a linear action, and then it is, if you wish, part of the so-called stringy diffeomorphism group, which is again a linear group in this case. So these are the key ingredients for double field theory, which was developed by Hall and Zwiebach, and then also by Olaf Hohm, who is now in Munich. With this, you can construct a manifestly OD, D invariant strict action, and in general, if you not only have one dimension but several dimensions, you use a covariant OD, D vector, which indeed comprises the coordinates or the dual coordinates and the coordinates in this way. I cannot give you so many details about this, so I just give you the answer first. What is the OD, D invariant double field theory action? And to get it, you introduce this big D, D dimensional matrix, so 2D dimensional matrix, which comprises the metric and the B field in a particular way. Then after some work, you indeed get this OD, D invariant double field theory action, which now indeed depend on both coordinate types, namely on the coordinates and the dual coordinates. So if you want to eventually recover, say, the standard Neville-Schwarz action, you have to set one part of the coordinates to 0, apply a so-called polarization constraint, and then after some work you get back the standard Neville-Schwarz action, which I have shown you before. But you can also do something different, and this was the key of understanding how to get the effective action for the non-geometric backgrounds. Namely, you can start with your original background, this is general, and then perform a certain field redefinition or certain OD, D transformation, namely basically the one which inverts this background, and then you decompose it again into the symmetric and antisymmetric part, and for the antisymmetric part you get now a B field, which is basically a two form, but now you get a B vector, something, a bivector, something which is like a vector with two indices, beta, and therefore it is called a bivector. Furthermore, you introduce now again also certain derivatives of this new object, of the new bivector, namely one object which is called Q, and this is simply the partial derivative of beta, and also a field strength which is a kind of really covariant derivative of this bivector. Observe that I don't talk about torsion classes here. I think one can relate it to torsion classes. but there is not at the moment relation to torsion classes. The whole subject of double field theory is probably closely related to generalized geometry, generalized complex geometry, and then you get the connection to torsion classes. But here I do not talk about torsion classes. I define just these two objects. Observe that R has all indices upstairs, which is basically an object which lives in the dual space, and indeed it is a good tensor, whereas this has still a mixed index structure, and one can show that this is not a good tensor in the space. It serves as a kind of connection. I think this will be explained in one of the further talks, maybe I think by Peter Patalong in particular, what are the geometric meaning of these objects. You can also formulate Bianchi identities in terms of these objects, because in order to get the right number of degrees of freedom. And finally, now you can do this field redefinition, yes, and just plug it in. You know a priori that you do not change the action, because it is an OD, transformation. So you put it in your action, you get a new action. Maybe I'm a little bit quick here, because also David will explain this more. Here in this rewritten action, in fact, now you have two Riemann to Einstein terms. One depends on the coordinate x, and another term which depends on the tildes. And you have also two terms, namely two quadratic terms, which contain this new object, these new fluxes Q and R in this way. And finally, this is what we call the final action. You set all the derivatives, the tilde, basically all the x tilde coordinates to 0. So you put in some constraint that you want your action only to depend on one set of coordinates, say on the x coordinates, and then you get the final action. And this now has a Ricci term, and indeed has various other terms, and the most prominent of them are these squares of the so-called R flux and the square of the so-called Q fluxes. So instead of the H field, we have now these new terms, and this would then require a little bit more work, but I could show it to you, at least for the examples which you have also introduced. The nice thing is now that in terms of these new variables, the action is now indeed well defined for geometrical fluxes. So this is actually our proposal, how the more general action, or how the alternative action for the non-geometrical fluxes should look like. It should replace the standard Neveu-Schwarz action, which you know with the H field. The new action is more involved, and I think it would be also quite interesting to see really what is the precise mathematical meaning, the precise mathematical formulation in order to get this kind of action. So my time is, I think, getting shorter and shorter. Maybe I can still speak about for another 5 minutes in order to explain you these other aspects, which I think is also very interesting and exciting, namely how these non-commutative and non-associative geometries arise in this context. And I think Ralph will also explain this more, and I think also Eric Plauchin in his talk tomorrow. So what we want to do now is to derive the stringy quantum geometry of these non-geometric backgrounds. And as I have already told you, it will turn out that you get deformed non-commutative or non-associative stringy geometries with these new fluxes, the Q flux and the R flux, as so-called deformation parameters. And to derive it, we now have to use a fully quantized string. So we have to include also oscillators and alpha prime corrections. And in fact, one can do it in two ways. One can set up a so-called mode expansion, oscillator expansion, and this is also the way I did it in my first paper on this. Or one can do also a worldsheet CFT computation. At the end, I think this should be completely equivalent, but I think today I like to introduce basically this kind of way how to derive the non-associative structure. So we will use this vibration spaces where we have a torus fibered over, say, a one-dimensional circle, and we have two T-dual cases. The geometric space, the omega spaces are the ones where only the complex structure is transformed by these transformations, which are called monodromy transformations. So this is a picture. If you encircle the base, let me see how to get the picture back. Yes, if you encircle the base once, the torus upstairs will be changed by a transformation which acts only on the complex structure. On the other hand, if you have the non-geometric space, the Q flux, you act now on the Keller parameter, on the rho complexified Keller parameter of the torus. So you have a transformation which acts, for example, in this way, that going around the base, indeed you invert the size, you invert the Keller parameter of the space. One specific example, these are called monodromy transformations. So now I want to realize this in an explicit string setting, and the specific example has so-called Z4 monodromy. This was also done in part with Cesar Condescu and Yannis Floakis. So this is a transformation which acts on the base, and indeed now I do it on the worldsheet. I shift sigma by plus 2 pi, and then indeed x3 is shifted in case I have some non-local configuration, namely a configuration which shows winding in this x3 direction. I told you for the omega space you have an action on the complex parameter tau. For the Q space you have an action on the Keller parameter rho in this way. And now you have to find out how this transformation not only acts on the background but also on the coordinates of the torus, which lives upstairs as a fiber. And here it turns out, when you do this transformation, combining, say, the torus coordinates to a complex coordinates, which I call x left here for the left movers, this transformation acts as a rotation, and the rotation angle theta is indeed determined by the flux parameter, I call it here h, and by the winding number n3 on the base. So it is a winding dependent rotation on the fiber coordinates, and you can now set up a corresponding string mode expansion which precisely reflects these closed string boundary conditions. So for this you are introducing twisted oscillators, so it looks very similar to an orbifold construction, and in fact it is very similar or closely related to an orbifold construction. And now the surprising thing, if you now compute the commutator, say, between these two left moving coordinates here in complex form, you see that the commutator is non-zero. It's given by this function which depends in this particular way on the winding numbers. You can do the same thing for the right movers, and here you have to be more careful, and this is crucial because for the right movers you have a different sign in this rotation angle, namely for the geometric space they rotate in the same way as the left movers, so like a symmetric orbifold. However, for the right movers you get precisely an opposite sign, so it looks like an asymmetric orbifold, which in fact it is. And if you now put things together, you see that the omega flux space, the geometric space, is still commutative in the torus. However, the non-geometric space becomes non-commutative, and indeed the non-commutativity is proportional to the winding number, which I call p tilde here. So for zero winding sector there is no non-commutativity, and of course it is proportional to the flux and also to the string length. So one can formulate also uncertainty relation. Maybe I skip this because I'm short in time. It is an uncertainty relation which indeed measures the winding of the string in the third direction. However, what is important, what I like to tell you, that indeed it does not only look like an orbifold. One can really realize these spaces, at least on some particular points in the modular space, as orbifold constructions. In fact, these spaces can be realized as so-called freely acting asymmetric orbifolds, and then the model really becomes completely solvable. It's a solvable, exactly solvable conformal field theory. For example, you can write down the partition function where I have not given you the details, and you can again verify that this non-commutativity for the asymmetric case arises. Now finally, and this is what I have mentioned before, now finally you can do also a formal T-duality in the third direction. This is at least the way I describe it here. I think the other way is also to get it, which means that we just replace the winding number in the third direction on the circle by the momentum number. So basically we are copying the same formula as before, where only the momentum number now appears on the right hand side of the commutator, and then you can use the standard commutation relation between P3 and X3, plug it in here, and then it's a very easy exercise that this relation indeed implies also the non-vanishing of the so-called Jacobiator or non-associator, namely that this double bracket is non-zero. This is indeed a non-associative algebra, which I think people call also twisted or deformed Poisson structure. Some parts of it are known to the mathematicians, and I think it's very interesting to investigate this further. And as I have mentioned already at the beginning, this indeed now very nicely agrees with the non-associative closed string structure which was found by Ralph and Eric in a different setting, though namely in the setting of the SU2 Wessel-Witten model in 2010. Okay. In general, you can also think or ask yourself, I'm almost done, how you can formulate this in more general terms, namely suppose you have a certain Q flux space or R flux space. Can we relate these non-commutative or non-associative closed string algebras to the Q fluxes and R fluxes which appears in the setting, in particular to those which I discussed in the context of doubled field theory? And indeed, I think this seems to be possible, and here's our proposal, namely that the commutator for closed strings is this particular line integral, so it looks like a Wilson line, similar to a Wilson line operator, and if you do it for the case of the one-dimensional circle, indeed you get back the winding number, which I have shown you before. And then for the R flux, I think it is natural to conjecture that this non-associator indeed is given by the expectation value of the R flux on the right hand side, whatever it is really at the end. And of course this part of the story is not yet completely understood. And I also like to mention, if you go back to some old literature, namely look at point particles in the field of magnetic monopoles, which is related to so-called co-cycles, you will discover very similar structures here, namely very similar non-associative algebras, which is something which was pointed out by Jacques already in the 80s. So let me very quickly give you the outlook and some of the open questions. I think this part will then now be partially covered by Ralph's talk, namely how you compute string scattering amplitudes in this non-geometric backgrounds, and this gives, I think, further evidence for the structures which I have explained you during my talk. This is the phenomenological part of my talk, namely I think they're interesting from the mathematical point of view, but eventually they might be also useful for applications, in particular in string cosmology, because you know for geometrical spaces it's very hard to get de Sitter vacuum and to stabilize all moduli in a satisfactory way. This might be bypassed for these non-geometrical spaces. I think these no-go theorems do not hold anymore here in this context. Of course, eventually we would like to know, is there a non-commutative or non-associative theory of gravity, something, a problem which was also already addressed by the group of Julius Wess some years ago. And finally, certainly since now we are dealing with non-associative structure, one needs at the end a generalization of quantum mechanics, because quantum mechanics is commutative, non-commutative, but still associative. And the question is how one can represent this algebra, for example by octonions or by some other objects, and I think this is also a very interesting and challenging question. So thank you for your attention.
So you showed that the effective action
for instead when there's H and when there's gauge and geometric fluxes, how we can also get an effective action for the case when there's Q and R fluxes. But I suppose generically there will be all 4 types of fluxes. What can one say about an effective action in that case?
Good question. This is something which we really think about a lot and debate also a lot. For me, there's no known example so far where there are both type examples for some particular background. So the examples I know at least, either of the one type or the other type. Of course, at the end, you might think in the most general case, there's a background which realizes this terminology H, omega, Q, and R all at the same time. And then I'm also a little bit stuck at the moment. I cannot give you a satisfactory answer. So I know this is in a way also how the construction is designed a bit, starting from one peculiar case, making a field definition or T-duality, go to a different frame, and then you get this action. But I think this is one of the important questions here.
Just something I didn't understand, I think, with the effective action. You started with a double field theory, and then at the end, you eliminated the X tilde coordinate?
Yes, that's correct.
So at the end, you obtain a geometric in a sense?
Yes.
So
at the end, I obtain indeed something which looks geometric because I do not want to use all the coordinates. I only want to use one set of coordinates. And now I have 2 options indeed. Either I can also throw the axis. Then I describe everything in terms of the dual coordinates. And then the action will be again very simple. It will be just R of the dual coordinates. The Ricci R, basically this term, plus R square, where H is basically only replaced by R. But on the other hand, if I want to capture this non-geometric aspect, which is in a way also due to, in a way, wrong choice of coordinates, because there will be, or apparently is always a frame where I can always formulate things which looking normal. If I decide to formulate the action still in terms of the axis, then I get this more complicated looking thing, which is, however, well defined in the non-geometric circumstances. And I think this is the important point here.
Yeah, so that was my confusion. You
Yeah.
can always go to coordinates and with the action it looks geometric.
Yes, in a way, that's correct. At least if I do this simple inversion of the field E, the background E, which is G plus B.
Last question. But it's a follow-up to that, because that confuses me. You began saying there are 2 folds, and then there's no global slice in which you can do it, and then you just ended saying I can always pick coordinates, so it's locally geometric.
Yeah, true, but still these are the x coordinates. So if you do this indeed for this T-fold example I have shown you, and you compute R of G tilde, the dual dilaton phi tilde, R and Q, only Q in this case, these are all now well-defined objects, and this new action is indeed well-defined. So we claim this is now the action for the non-geometric background, indeed. And the Q flux case is indeed perhaps even more interesting than the R flux, because the R flux is a completely dual of the H, but the Q is a mixed case. And therefore, either way, if you do the polarization, if you express everything in terms of X or X tilde, you get a new looking action.
Okay. But shouldn't there be things which can't be expressed as with one global slice through NPD? There must be stuff that doesn't have a global section.
I think then you are entering the question Diederik was asking, namely, are there situations where you have all these fluxes at the same time?
So we've shown that there are supergravity models which have exactly this property, which cannot be T-dual.
Yeah, but these are effective supergravity models,
Absolutely.
I believe, in 4 dimensions. And then still is the question how to lift them to 10 dimensions. This is in 10 dimensions. In 4 dimensions we know that there are gauge supergravities where all the fluxes are present, but I still doubt a little bit whether one can lift all this to 10 dimensions.
So you use the double formalism in deriving this,
Yes.
which relies on some toroidal structure, right?
No, maybe I forgot to say this T-duality, this double field theory, and this is a nice and interesting thing, doesn't rely on any background assumption. It is background independent. It originates from string field theory, and it even doesn't rely on the assumption that there are isometries. And therefore, the procedure is legitimate even in the case of the R flux, where there is no isometry. This is, I think, a very nice point, which was, I think, observed by Zwiebach and Chris Hull. Therefore, the whole system is background independent, and therefore I think it is really a very, very nice formalism.
So this action depends on whatever I throw in there.
Yes, you can do it for any background.
But if it is non-geometric, what do you mean by that?
If I talk about non-geometry, then of course I'm considering certain backgrounds, but the transformations which I have shown you do not rely on a background choice.
When you go back to in the duality, for instance, for X3, when you're dualizing X3, there's no symmetry. How can you go back to the original one?
What is the question?
When you dualize with respect to X3?
Yeah, this one.
Yes. There's no symmetry. How can you get back to any of the starting point?
Well, the point is, if you follow the prescription of double field theory and dualize x1, x2, and also x3, but express everything in terms of tilted coordinates, then it looks again like your ordinary Schwartz action. So indeed, the prescription works, but I think there are, on the other hand, admittedly, no good example where you can construct what is the R-flux as a function of the untilted coordinates. I think this is also not really known, that because this would then really require that you apply the Buscher rules of T-duality, which are now background dependent, and then you would try to get the R-flux as a function of X3, but this is not possible. It exists in the dual framework. It exists also, say, in the CFT context. Maybe Ralph will talk about it as a kind of asymmetric, left-right asymmetric construction, which is also true in the example which I have shown you. But as a function of X3 doesn't exist, this would be also in contradiction, because the claim is that the R-flux background cannot be described locally.
Can all these things be useful for understanding, for instance, not abelian T-duality, where you don't have isometries?
Yes.
Has it been done?
Not really. No. Maybe David.
There are people trying.
Yeah, you know maybe more about this, but I don't know.
People are trying.
Mm-hmm.
All right. Maybe one last question.
Can you supersymmetrize the action that you obtained?
Excuse me?
Can you supersymmetrize the action that you obtained?
This is obviously the bosonic part of the action, and indeed it should be possible. Of course, there's an issue with T-duality and supersymmetry. If you want to preserve T-duality at least linearly, then you have to have also, it has to commute with supersymmetry. There are also cases where supersymmetry after the T-duality is realized non-linearly. This was worked out also by people, so I think supersymmetry is an issue, but I think this can be worked out at the end.
Right, so let's thank these guys.